Good afternoon. Welcome to Navigating Nano podcast. I'm your host, Faith Zablon, and I'm honored here today to have Dr. Lilian Hsiao from North Carolina State University. Welcome, Dr. Lilian.
Thank you.
It's wonderful to have you here, and I can see you are an associate professor in chemical and biomolecular engineering. All the other things you're going to tell us a little bit about, yourself. So could you just break down what your CV is about?
Sure. So actually, I was born in Hong Kong, and I've been in the United States for a long time, over 20 years now.
Okay.
And my undergrad was from Wisconsin-Madison. I did my degree in chemical engineering there, and then did a Ph.D. in chemical engineering as well at Michigan, and then did a postdoc at MIT, and then started at North Carolina State in 2016 as an assistant professor.
Okay.
So I'm very happy to be here. And I'll tell you a little bit about what we do in terms of research as well. And I don't know if that's the question you will,
No, we'll get there.
Okay.
You just mentioned MIT, so I did see that you're postdoc from MIT. How was that experience? Everybody wants to go to MIT. I want to go to MIT. How was that experience?
So I think MIT is a great place. It's in Boston, right? So it's in Cambridge, Massachusetts, right next to Boston. And so the environment is very different in the sense it's a big city.
Yeah.
So if you like living in big cities, that's one of the great places to be. It's very vibrant, full of young people, a lot of people in startup companies, in pharmaceutical industry, in consulting. So it's got this energy about it. And going to MIT, I would say a lot of people tend to be a little bit nerdy on the nerdy side, right? Rightfully so. And once you're in, you feel that actually everybody wants to help you, right? They actually, well, there's a little bit of that energy going on as well. I'm not going to lie, right? There's some competition, but overall, I feel like everybody just wants to get really good research going, and if you show some energy that matches theirs, they're often very, very happy to help and try to get you to where you need to go. So I would say, as a postdoc, I don't know how it's like as an undergraduate or PhD student, but as a postdoc, it was a great place to do research, and I could really focus on doing cool things that, interest both my PI at the time and also was of interest to my own, my own interest.
Yeah, in terms of networking, in terms of mentorship, how was that experience for you?
Network was great. There are a lot of postdocs and graduate students there.
Okay.
A lot of undergraduate students there as well. So I got to, I still am friends with many of them. I see them at conferences. We will go out for lunch, dinner, coffee. And actually, I have a good friend who was a PhD student at the time in the lab, and I helped him a lot with 3D printing and just troubleshooting a lot of his system. And he was, he needed some help at the time.
Okay.
And so we still, text each other. We meet up when I go to Boston, and he works at a startup company. It resulted in some professional consulting opportunities as well, and which I'm very grateful for.
Okay. Yeah. And you a nerd? You mentioned that people in MIT are nerdy. Are you a nerd?
Maybe.
Okay.
I am a cool nerd. But if you really want to get into the nerdy parts, I can get quite nerdy.
Oh, okay.
Yeah.
So now,
yeah. Comes with practice.
And you mentioned that you came from Hong Kong 20 years ago. So let me assume at this point in your life, what was your level of academic experience by then?
I was born in Hong Kong, and then my family moved to Singapore for my middle and high school. I would say my academic experience was, like in the sciences. I actually, recently somebody, a young kid that was on campus saw, I was just walking my dog, and they came up to me and they asked me, have you ever failed any classes before? And I said, yes. Without hesitation, but it was in history. Thankfully, not in any of the sciences. But I was never very good at the humanities, unfortunately, even though I tried. It's not for lack of trying.
Yeah, and having these American experience, and you have been exposed into academia, now you're a researcher. How does that compare to back home in Hong Kong?
I don't have a basis of comparison of how it's like to be in college or do a PhD or even to work there. Simply because I didn't do that.
Okay.
So I would say, I think in the US, people really value creativity. They value this kind of balance between, like nerdiness, right? Versus doing something fun or something sporty.
Yeah.
And that was not an experience I had. So I think in Asia, they tend to have this attitude where, you should wake up in the morning. And so I remember in school, my everyday schedule would be, I wake up at 6:30 in the morning. My mom would give me breakfast. And on exam day, she would give me a special thing. I won't mention what it is, that is supposed to make the brain work better for that day only.
You have to tell us what that is.
I don't know. Anyway, it might gross some people out. But anyway, so then you eat this thing, right? And then you go take exams. But most of the day is just, you go to class, right? There's a PE class, of course, but then most of them are like, classes that are 45 minutes or so. And then you spend the whole day basically, there are some activities that you should participate in, like sports or music, clubs. And then you come back and you do homework. And then you have projects that go all the way until maybe 11 p.m. And then it repeats the next day. Okay. At least that's my school experience. So I think I would have liked it if it wasn't as kind of packed like this, where there's more time to develop friendships and, go out and do stuff, which, there were times that we could do that as well.
Okay.
Yeah.
Well, you seem cool. You seem to have a
you.
personality where you can make friends.
Thank you.
naturally. Yeah. So that is about you and, your personal experiences. Now we want to dive into the science. And I saw in your profile, you're a soft matter mechanic. So in terms of the research, could you tell us what this is about?
Sure. So at a very high level, soft matter is anything you would consider soft. Like, so for example, the couch we're sitting on is actually made out of foam, which is a soft matter. The leather is a soft matter. I mean, we're made out of soft matter, which is like tissues. We're mostly liquid, right? Like we have a lot of water in our bodies. Hydrogels are part of our research.
Yeah.
And the word hydrogel means water gel, right? So these are systems that would grow tissues on them. They're used in 3D printing, for example, and you can do a lot of functionalization. So that's an example of soft matter.
Okay.
Other types of soft matter that people maybe don't think about at a very careful level is, the food that you eat, the creams that or lotions that people put on their skin, the products that are sprayed in fields to make crops grow, to make plants flourish. And so these are also examples of soft matter where the component's actually hard, like it's sometimes made out of polymers and sometimes made out of metals. Like paint on the car, for example, is an example of soft matter. And the reason why we call them soft is because these liquid particles that give it the shine, for example, like gold or silver, actually small particles that are suspended in a liquid, and when they flow, they have some really unusual properties, and that's also classed as soft matter as well.
Okay. Oh, that is very interesting, to be honest. I wouldn't have thought that far, but you have explained it in a very simple way. So what does your research group focus on in terms of soft matter? So you have given us this picture, but what do you focus on in your research?
We do a few things, different things that are pretty interdisciplinary, but mostly just focus on soft matter. One part of our research is actually very industrial focused in the sense that we are sponsored by pharmaceutical companies and some other petrochemical and agrochemical companies where they want to look at how to, for example, let me use vaccines as an example. So we have a project on vaccines, but it's not the biological aspects. It's more like how to make it stable. And this is also something that patients don't really think about, but industries have to because, for example, you have a flu vaccine. And so the vaccine usually comprises of some particles that are suspended in a liquid. And when you go to the clinic, what the nurse or the clinician will do is they kind of invert this vial to try to shake it up, right? To make sure it suspends so that they can get it into the body. And what we're studying is that how do we make this very complex solution containing proteins and other adjuvants that they add actually resuspend properly so it doesn't clump and it doesn't, it should redisperse properly. And that is actually a very long-lasting, a very long-standing, and very difficult problem because you have all these interactions between proteins with the particles that they use to stabilize the proteins, and they often have these attractive interactions, which can give rise to sometimes irreversible formation of clumps. So that's an example of one of the projects. We call them colloids. These are very small particles that are bigger than nanoparticles. So that's one area of our work.
Your work. And I know you've talked about the soft matter and you mentioned 3D printing. Could you kind of integrate those two and how you're applying them in your research?
Absolutely. So in 3D printers, we actually use a very cool material. It's a oil and water emulsion. And these are suspended in hydrogel, so they can be turned into hydrogels that have little oil droplets in them. And you might be wondering, like, why do you put these oil droplets in them? And one thing is also pharmaceutical and delivery driven. So we were trying to commercialize them for burn dressings. And the reason is you can encapsulate all kinds of different things that would otherwise be not miscible with each other. So just think of oil and water, right? They don't mix.
Yeah.
But in this particular system where you use 3D printing, you can actually print any shape you want that flexes, or in really any shape you want, conforms to the body or conforms to any object, but still have this functionality where it can contain things that are completely immiscible, that have maybe healing properties, or maybe it delivers nutrients in some way to the cells or to the body. But normally, if you just mix them in a vial, or a test tube, they would just separate.
Yeah.
And you can then 3D print these things to, for example, put on a patient that has, is suffering from some skin problems, right? And it can deliver at a certain rate that you want over, for example, 2 weeks. So that's what we do with 3D printing. We basically get them into different forms, and some of them are used for plants, right? Like you can deliver drugs onto plants. They need very small particles, for example.
Wow, you seem to be doing a lot. And what you're mentioning, you've talked about drug delivery. So is that an area of specialization in your interdisciplinary research in your lab?
Yes, that's one of the 3 areas that we work in.
Okay.
So the first one I told you was on different colloidal resuspension and interactions between them. The second one I told you, we do a lot of 3D printing with soft materials, and we try to make sure they're sharp and of the size that you want. And another one that I will talk about today is on tactile sensing. So these are also, you really need soft materials, right? Yeah. A lot of sensors that everybody wears on their skin, like a watch, it's right now it's a silicone or some kind of hard material, and it can be a little uncomfortable sometimes. And so we're actually taking this a step further. We're trying to use biopolymers, which are extracted from like seaweed, and alginate, for example, is extracted from seaweed. And they have these they have these ions in them that allows them to transport a current. And when you press them, for example, they can kind of, they are very comfortable to start with on the skin because of certain chemical properties that we design. But they can also carry current, and we can use them as sensors for sweat sensing.
Yeah.
For, if you move your joints a certain way, it can tell you, oh, here's the voltage, right? And that's a very important thing for generating films that are used for electronics in the future.
And wow. I'm very impressed by the fact that you talked about, you can use them as wearable sensors. And how do you envision? Okay, I think I have a couple of questions there. So there's the merging of the research that you're doing and industry, right? And then how do you envision this technology evolving over time? Because here we do have students who are working on wearable sensors, and I think they'll be very interested in what you're about to discuss. But how do you envision this work being translated from your lab, into applications in real life?
Yeah, that's a really great question. So my labs, my students work on a lot of more the fundamental aspects of these problems. Like, I'm not getting deeply into it, but we look at like physics and the chemistry of how things interact with each other in order to give them the properties that we're trying to target. So we're at that level. But another way to make them translate to technologies that people use is we have a startup company, and we're working on some hydrogels, for example, like the 3D printing problem. We hope to be able to fine-tune some of the formulations that clinicians might need, make sure they actually work, right? Like that's a big part, like making things work in the lab first, then work at a higher level, like scale up. Like I'm a chemical engineer, so our training is all on scaling up. If a chemist might be focused more on like how do these things interact, and we're like, okay, does it scale up? And once you scale up, then you can think about commercialization. Does it make money? What's the economy of this? Is this recyclable, right? In a sustainable economy, that's super important. And so these are considerations that, as a startup company, people like students or staff that work in that can focus on. And that's not what we do in our lab. We still focus more on what makes things work.
Okay.
But that's a very easy route for students and postdocs to be involved in if they want to see a technology go to like become a bigger part of different big companies.
Yeah, I have a lot of questions, but let me open the floor to the audience.
Okay.
Yeah.
What type of 3D printer do you use if you're allowed to disclose that?
Yeah, so we purchased from Cellink, which is a company based in Boston. They actually, I think, were a startup company. And we bought this bioprinter. It's called the BioX6, and it's a printer that actually you can print cells in. That is designed for cells. We don't do cells at the moment. And so there are these little syringes that you can fill with ink, bio inks that you like. We fill them with our nano emulsions, for example, and you can control temperature. You can control the flow rate, right, pressure drop, and you can print anything you want onto a stage. It has a UV cross-linking module. Yeah, it's really, in its essence, it's just a syringe that's being pressed. So that's the cartridge that you use. Yeah.
Okay.
Now there are other types of 3D printers. For example, Formlabs also make a printer that's called a stereolithographic printer. I know that some companies use them, like Carbon, for example, also makes these printers. But what you do is you have a pool of ink, and it uses these lithography methods where you shine light into the pool. It cross-links the ink, and then you pull a stage up, and that's how you get the object. That's also another printer. It typically is more expensive than just the syringe type. Yeah.
Hi. So you talked about like sweat and sensors and things of that nature. Can you talk a little bit more about what you guys do in your lab pertaining to that, and then maybe talk about whether or not you take the glucose oxidase route or something more unique to your lab?
So we are more of a physics-driven lab. So that's my way of saying our chemistry is not probably as good as yours, right? So the sensing that we try to do is right now, the talk that you will see later is more on some of the physical aspects. So for example, how patterns will interfere with, like if you have water, which is a very common problem in soft robotics. For example, like if you think of a robot trying to operate, like trying to move something around, they're often designed, like this is more a mechanical engineering problem. They're often designed to overgrip, which is they think it's a dry object, and you have a force, your hand does this, right? And it needs to hold it like in a certain way. So how can we more intelligently, or first, like what are the principles of this force, which is very important that most people don't even think about because we know them as children. Like we're taught as children how to hold a dish so it doesn't fall out of your hand. But the robot doesn't know how to do that. So what are some of the physical principles of soft materials, and such that they can first hold on to something, and how to make them comfortable so people will want to wear them, because a lot of these soft materials are actually very sticky. But if something is sticking or scratchy, nobody's going to want to wear them. So some of the chemical aspects of migration of molecules onto surfaces and how we can engineer some of that. But the sensing part is something that we're currently working on. It's unpublished work. There's a few graduate students working on this. So we use these hydrogel sensors that are very sensitive to ions, in particular just sodium and calcium. So the presence of any sodium, even a minute amount, can actually influence the mechanical properties, like they start to uncross-link. And by measuring the physical properties, you can sort of say, well, the concentration of sodium to calcium is now at this level. So we're at that level of chemistry. We don't have more sensitive, in terms of chemical sensors, it's not more sensitive than that at this moment. But often people will functionalize the gel to basically react in a way to the molecules that you mentioned that are of interest, and that's something we would love to look at in the future, like the next 2 years or so.
Okay. It's very interesting about what you're talking about. And here we do have some students like looking at the wearable sensors, but they're looking at materials. Probably they mixing or integrating the hydrogels with materials. Do you have that kind of research going on? Like,
yeah, right now we use elastomers, which are, these are polymers that have very strong, robust properties. They are the ones that use, because we used to collaborate with some soft robotics groups. So they use elastomers because it doesn't deform, it doesn't stretch out.
okay.
And so that was very good for them. Now, in terms of mixing with hydrogels, I think it's doable. Often there are blends that you could use.
Okay.
The main thing is whether it's miscible or not. Oftentimes, hydrogels like water, and a lot of polymers don't like water. So that's actually the step 0. You have to solve this particular problem.
Okay.
So I'll give you an example of something that one of my grad students, who's actually he's from Nigeria, and he came from Nigeria undergrad, came over and I gave him this project where he should be grafting this, it's called polynipam, so poly-N-isopropyl acrylamide, I think that's a full chemical name. It's responsive to temperature, and pH. So through some chemical grafting methods, he will graft them onto the surface of elastomers, but that will imbue it with some properties that are kind of mixtures of hydrogels, which is the polynipam, and elastomer base. And that gives it some temperature responsiveness. The elastomer, some temperature responsiveness.
Yeah, which you can use on skin, right?
I would say so polynipam is, I'm not sure if it's FDA approved,
Okay.
but PDMS, the elastomers typically are, like we actually encounter them in a lot of everyday life. So they can be used, and they are used in wearable sensors.
Okay.
So isn't it the polymer they use for electrospinning a lot?
The electrospinning, you can do that. You can spin you can spin most polymers. PDMS, so polydimethylsiloxane. I mean, actually, if anybody has an Apple Watch or some kind of electronic watch, the bands, that rubbery band is usually made out of elastomers. Elastomers are also used in caulk. So if the bathrooms, the waterproofing part is an elastomer.
Do you know anything about 4D printing?
So yes, 4D printing, as far as I'm aware, started from a group in Harvard. So by Jennifer Lewis, who I applied to postdoc with, and I'm very familiar with her work. So they actually, what they mean by 4D is, 3D printing is like you can print in XYZ, right? So you can print like a stack, for example. And 4D printing is, in its initial implementation, there was I think a Nature paper on this. You basically like soak it, or you put it in some fluid or something like that, and so it expands to the shape that you actually want the object to be in. I'll give you an example. So I am into like clothes, right? Sometimes I buy sweaters, you put them in the washer, and you're like, oh no, it shrank.
Yeah.
So that is an example of the 4D, like either shrink or expand, but to the shape that you actually want. So that is the. Well, you can buy extra large or pre-shrunken textiles.
How you go and you have those towels that are like small, and then you put it in the water and it grows into like.
Exactly. So that was the first implementation of 4D printing. I think there are some like other things that are more specialized now, but that's my interpretation of 4D. Yeah.
Okay.
So I know we touched a little bit, I'm going to kind of talk about electrospinning, but you also talked about the polymers. And I noticed in your abstract, you kind of referenced extreme conditions. So what are you guys, or can you touch on the things that are going on in your lab to deal with extreme conditions, and which extreme conditions you're referring to? So in terms of extreme conditions, we just meant that there's water, right? And it doesn't sound extreme to a human, right? Because we're so used to it, but it's pretty extreme to mechanical engineering people. Because they don't, usually a lot of these, like we learn in textbooks, it's like, okay, here's the force diagram, right? Like you learn in statics and dynamics, which I think is an undergrad but they don't actually tell you what happens at the interface. And so actually most of the textbook things that they learn in school, like the moment there's something going on at that interface, whether it's like dirt, right? The presence of dirt, the presence of, some slimy things, right? Like in dirty environments, when there's fluid moving really fast over it,
those things will all kind of mess up the traditional understanding of how to control force. So in that sense, we're adding something that humans know how to do very efficiently, and trying to make sure that in the next generation of, virtual reality or like robotics, that they can also mimic some of the things that we kind of take for granted in extreme environments. So that's one of the, we look at things like high pressure as well, but those are more specific cases to suspensions that have to undergo processing.
What about temperature?
Most soft material, especially hydrogels, water boils at 100 degrees. So that's probably the most extreme you can get, 100 degrees. So we do temperature, like in that sense, I would say it's not that extreme. So we just see if, hydrogels will react or fall apart at these high pH conditions. How do we stop them from doing that, right? Just to maintain their integrity, which is a very important applications, because you might even think, okay, even for cells, right? Like, or humans or animals, anything above 37 is dangerous. So that would be extreme for animals. But the same thing happens with a lot of synthetic materials. With water in them, you have to be careful it doesn't evaporate, because the moment it evaporates, like a wearable sensor, this is a problem that we're trying to tackle. Wearable sensor made out of a hydrogel. Okay, how do you stop the water from evaporating? A simple thing, right? But it's not a simple solution. Actually, very challenging solution. So things that we're trying to look at is like vapor pressure, right? Can you make some fluid that is like water, but doesn't evaporate? So sugar is an example. Sugar water doesn't evaporate. So that's how we're trying to overcome some of these intrinsic problems.
Very deep physics, like those are things that we barely think about.
Exactly.
Like, the interface of the skin and whatever you're wearing. Yeah, very exciting. I'm going to shift the dynamics a little bit. And I saw that you won several awards, and congratulations. You have been recognized for very prestigious kind of awards. I'm interested in the NSF Career Award, and we are in that phase of transitioning into early career researchers or becoming, professors at some point. Could you tell us a little bit on how this award has enabled you to advance the science or the research that you're doing, and how can you advise us in applying for this kind of awards, in future?
Yeah, so first I have to really thank my students, because a lot of these awards are based on their early efforts that may not be published at the time. So a lot of data has gone into writing grants. For the NSF career in particular, we only got it, actually I only got it after the third time, right, of trying it. Okay. So first, I think the general advice is, okay, the NSF career is a really wonderful program that the National Science Foundation, based on taxpayer money, are used to support young faculty before tenure. And what it does is, if you get this award, you can basically have the freedom to explore some of the things that the person wants to explore. In that case, we were trying to move into the haptics and tactile sensing, which is not an area that I did during my PhD or postdoc time. So it was more difficult. Without the monetary support, I think it would be more difficult to get that going to the stage that it is today. So I would say it has given me the freedom in terms of exploring topics that I think are very important and are still kind of like cutting edge.
Wow, very, very interesting. And out of these awards, how many publications have you had?
I think we have 36 or 37 at the moment.
Okay. That's wonderful. And can you say that being a recipient of these other awards, like Camille
Dreyfus, yeah.
Yes. How have they kind of enhanced your innovativeness or innovation, or advanced your innovation?
Right. Many of these awards are somewhat different from the others, right? The NSF career is a big grant, and I'm very thankful for that. So for the Camille Dreyfus and the Sloan Research Fellowship, I think they also come with some small amount of money, and these are often used to support students that are doing things that are not in grants. Like, for example, some of our projects is like very specific. You have to deliver this by this time. For example, with the pharmaceutical industry. But what these awards do is, like, let's say someone is interested in something crazy, like, environmental remediation. So one of my students is a civil engineer. And she told me really in the beginning, she said, I want to do something in sustainable, like something related to sustainability. And I'm thinking, we have elastomers. I'm not sure how sustainable they are. We're not chemists. I don't know how to recycle them, right? So I just kind of like sat on that thought. But now that she's in her third year, I'm using some of these award like money, which doesn't come with any stipulations, just that you use it.
Okay.
And I said, why don't you look at these hydrogels and how they can be used as membranes for PFAS removal? And so that's one of the things. She's making these small little beads. They have functional groups in them. They can be used for antibacterial applications. We have some data on it. But that's all supported by some of these smaller sums of money, which then goes towards her tuition and travel.
Yeah, that is wonderful. And we are about to finish. And when we are about to finish, we get into now. You as a PI, you are a mentor.
Yes.
It comes by profession. How do you cultivate the mentorship kind of environment for your students? How many students do you have, and how do you cultivate that long term? And foreseeing that maybe students are going into industry, or maybe some of us may end up being faculties. How do you nurture that long term for this student?
Yeah, so I learned most of my mentoring from my mentors, but I also put my own kind of personality and spin on it. So I found that everyone is different, right? Different people have different personalities, they have different needs, they have different family situations and life situations. They come from different backgrounds. And so I have currently 11 graduate students in my group, and one just graduated. But what I've found is that it's probably better just to set things up front as early as possible and as frequently as possible. So I meet with my students every week when possible. And oftentimes casually I'll be like, oh, are you still thinking about getting an industry job after you graduate? And if they say, yes, I definitely want to get an industry job, I'm like, have you thought about how this could be commercialized, or how this is relevant to the industry? Maybe try to tailor it that way, right? These are some of the encapsulation ideal, efficiencies and so on. Can you calculate some of that? So actually the project will shift a little bit based on what they want to do later, at least based on that point in time. But if someone says oh, I really want to go to academia, and I'll ask them, do you like teaching, or is it the research that you like? Because there's usually different tracks there. And then they'll say something, okay, if you're interested in teaching, we have these teaching workshops. Make sure you attend those, right? Try to shadow somebody and become more involved in their teaching the class, right? So that you get a sense of whether you like it or not. And they can say they don't like it, right? Absolutely okay. Then it's okay, let's revisit. Okay. And then if they're interested in the research route, I'm okay, here are some of the requirements, the papers, right? You need to have lots of publications. You need to go give talks, right? So I'll give them the opportunity. Sometimes they'll do internships, but at another person's lab, a big lab, for example. So often I'll talk to my students. We have a very good most of us have a very good relationship. Okay. And this is something I ask them often. It's do you still want to do this, right? What do you think? Do you like your project? Do you like certain aspects? Do you not like certain aspects? And then we kind of, through our weekly discussions,
you tailor
move, move a little bit, pivot a little bit here and there. It just depends on the person. Okay. Yeah.
And just to finish up before the other question, collaborations. What you have talked about, you even have a startup. How have you been able to establish those collaborations and even sustain them up to a point of having your own startup?
Yeah, oh my God. So this is a great question. So the reason why I picked North Carolina State University over other job offers that I had at the time in 2016 is because of the collaborations and the strength of the soft matter community in the Triangle area, so Duke and UNC Chapel Hill. But I'll just speak to my own department because I'm in chemical engineering, and there are 6 or 7 of us that do different aspects of soft matter in that department. And it's been great in terms of, I co-advise students. So let's say one of my students doing tactile sensing actually co-advised between me and Dr. Orlin Velev. So he gets kind of two sets of two bosses, if you will, but also comes with 2 kind of backgrounds and expertise, right? Exactly. So he gets all the training that he's looking for.
From both.
And then he can work in both labs, basically natives, right? But also in terms of working with other groups, we're in the same hallway, same building. sometimes we'll go for coffee. It's like, oh, have you thought about, this polymer aspect? Oh, that's a good idea. Like, let's try to do something. Or the students will do that. They go for lunch and they go to some party or something. And one person will say, I need some help with electrochemistry. Can you help me with this? I need some help with imaging. Can you help me? And that's how the collaboration starts. Okay. And then if it turns into a project or a publication, great. If it doesn't, that's fine too. Okay. Like, we're happy to help other people.
So the collaborations are more internal?
Yeah, it's like an organic way, right? Like, what I found is that it's very important who you work with. So you can say, wow, this person's CV looks like I could really collaborate with them on this aspect, right? And I would say 90% of the time, it doesn't work that way. Like, you can try to, you think it works, but when you start working, you realize there are certain things that may be not apparent on paper. Personality being one of them, right? Or the level of the career level, right? Like, some people need to graduate. So if they're graduating in a month, if you try to collaborate with them, they're graduating. So there are just little like environmental situations like that are not always apparent.
Okay. Just to finish up, how do you think your work, the work that you're doing, can contribute to the broader scientific community, in terms of innovation and translation?
Yeah, so I like to think that we do science at a level that's pushing the frontiers. Okay. We're generally pretty creative in terms of merging. What happens is in some science fields is that people are so focused on one thing, or they just don't know what's going on outside, right? Yeah. Like they don't know. Oftentimes we'll find, oh, they've solved this problem that we've been trying to solve for 20 years, like this other field, right? Like, why don't we apply it? And that's actually my first paper. This is why I actually wanted to go into academia. So I was like, wow, like we can actually take what somebody knows and apply it to the unknown. Exactly. And it's a big, it's a big deal. So in terms of that, we're still doing that in our lab. We're trying to, do different mixes, right? Like different mixes of things. We're trying to make sure they are relevant. We often meet with the industry partners like every 2 weeks. It can be a little stressful, but we often ask them, is this what you want, right? Like, is this relevant to your process? Okay. And then they'll give us some like material or some new advice. It's like, oh, we actually have a problem with this. Like, can you look into this problem? And that's how we also pivot projects specifically to address these forefronts of what people need in the industry. Yeah. In terms of like, we have a startup, for example, we're trying to commercialize some products. So these are some of the innovations that we're trying to push in our lab.
I think what you're doing is extremely creative, and I'm looking forward to listening to the talk that, you're going to give us. And very impressive work that you're already doing, and we wish you the very best as you move forward. Now I'm going to ask you a question from the previous speaker.
Okay.
And which you're going to do the same to the next one. And we try to keep it very casual, very human, because we try to humanize professors, researchers. Yeah. Yes. I don't know if this is going to humanize you, but yes. How do you balance work as a professor and family? There is another assumption that you have family. How do you balance work as a professor and family?
I think you have to be intentional. And I don't think this is very specific to professors. It is anyone that has a thing that they really like. And it doesn't even have to be professional. It could be a hobby. So you could sink 24 hours, 7 days a week into that hobby, and you would certainly neglect your friends and family. And this is something I actually learned during my postdoc. I had a really good friend from childhood, and she was not in academia, but she would often say, well, like, I'm a little tired of hearing about your work, right? Like, I think it was because I was talking about work all the time to her, right? So to be fair to her. And so there were some issues there. But I think what I learned was that, okay, like, I need to spend more time prioritizing friendships and family, right? My family, even back home in Hong Kong. And so I think it's just deliberately having to remind myself, like, oh, you haven't talked to this friend for like a month, better call her, right? Like, better call her and see what she's up to. Okay. Or, I have a partner right now. It's like, he's also busy. He works full-time job. And actually, he's much better at this than I am. Like, he has way more friends, right? And he spends his weekends socializing. So sometimes I'll be like, okay, be more efficient with my time. Like, work from 9 to 5, but don't go on Reddit or, try not to spend too much time browsing the internet, online shopping, looking at news. Try to reduce that, at least during the workday, like 9 to 5. And then go home and have dinner, right? And then make sure I call the people that are important to me. Talk to them, and then, try to structure my day in a way that I don't feel bad about not having done work. Okay. But I also don't feel bad about not having called the people or talked to the people that are important to me. Wonderful. That's how I try to do it.
Yeah, you have to be intentional. I guess every relationship, you have to be intentional. Make the time.
Yeah.
Then you're going to reap the benefits.
Right.
So thank you so much, Dr. Lilian. It's been wonderful to have you talk, and you sound very exciting. And I'm looking forward to listening to your talk.
Yeah,
this has been Navigating Nano. Subscribe and follow us on LinkedIn and Facebook and Apple Podcast and Spotify, where you can find us. Thank you so much.
Thank you.